Mechanics. Lecture 2. Reduction of movement in the central field to one-dimensional movement. Part 1. Basic characteristics of one-dimensional motion. One-dimensional motion is the motion that occurs along one straight line. The force acting on the system is directed along the same line along which the system moves. The solution of equations of motion includes the square root of the difference between the total and potential energy of the system. Since the expression under the square root must not be negative, the total energy of the system greater than the potential energy. So the motion of the system is possible only in those areas where its total energy is greater than its potential energy. So the points at which the potential energy is equal to the total energy determine the boundaries of the area of motion. Upon reaching one of these boundary points, the direction of the system's motion changes to the opposite. These points are also stopping points, since the velocity is equal to zero at them. One-dimensional motion can be finite or infinite motion. If the area of motion is limited by two boundary points, then the motion occurs in a limited region of space. Such motion is called finite. Limited region of space in which finite motion occurs is called a potential well. The area of motion is not limited if there are no boundary points in the solution of the equation of motion at all. If the area of motion is not limited or is limited by only one point, that is, only on one side, then the particle goes to infinity. Such motion is called infinite. One-dimensional finite motion is always oscillatory. The particle makes a periodically repeating motion between two boundary points. The period of oscillation is the time it takes the particle to travel from the first boundary point to the second and back. Part 2. Centrifugal energy. The motion in central field can be considered as one-dimensional motion in a field with some effective potential energy. This effective potential energy differs from the real potential energy of the field by a term called centrifugal energy. Centrifugal energy equal to half the square of the angular momentum divided by the mass and by the square of the radial coordinate of the particle. This centrifugal energy is always present when the angular momentum is not equal to zero. Thus, the effective potential energy is equal to the potential energy of the field plus the centrifugal energy. Note that the centrifugal energy in the center of the field tends to infinity. The tendency of centrifugal energy to infinity in the center usually leads to the impossibility of a particle falling into the center of the field. A particle can fall into the center only if the potential energy in the center tends to minus infinity quickly enough, thereby compensating for the tendency of the centrifugal energy to plus infinity. Part 3. Boundary points of the region of motion. In one-dimensional motion, the particle moves between the maximum and minimum values of the radial coordinate. There is maximum and minimum values of the radial coordinate. These values are boundary points of the region of motion. The maximum and minimum values of the radial coordinate can be calculated from the equality of the effective potential energy and the total energy of the particle. At boundary points, the radial velocity of the particle is equal to zero. Unlike true one-dimensional motion, zero radial velocity does not mean that the particle stops, since the angular velocity of the particle at the boundary points is not zero. Equality of the radial velocity to zero means the turning point of the trajectory, at which the radial coordinate changes from increasing to decreasing, or vice versa. Part 4. Finite and infinite motions. If the region of admissible values of the radial coordinate is limited by only one boundary point, then the particle's motion is infinite. In infinite motion, the particle comes from infinity, reaches the boundary point, and then goes to infinity. If the region of admissible values of the radial coordinate is limited by two boundary points, then the particle's motion is finite. In finite motion, the particle's trajectory lies entirely inside the ring bounded by circles with radii equal to the minimum and maximum values of the radial coordinate. Finite motion in the central field have an oscillatory nature and is carried out between the maximum and minimum values of the radial coordinate. The oscillation period in finite motion in the central field is a period the time after which the particle returns to the initial value of the radial coordinate. Part 5. Non-closure of trajectories of finite motion in the central field. While the trajectories of finite truly one-dimensional motion are always closed, the trajectories of finite motion in the central field are not necessarily closed curves. The non-closed nature of trajectories in finite motion is due to the fact that during the time equal to the oscillation period, the radius vector of the particle rotates by a certain angle. The particle's trajectory will be closed only if after a certain number of oscillations the particle will return to the initial point of its trajectory. So closed trajectory is possible only if the angle of rotation of the radius vector is a multiple of 2 pi. Thus, in the general case, the trajectories of finite motion in the central field are not closed. Part 6. Central fields with closed trajectories of finite motion. There are only 2 types of central fields in which all trajectories of finite motion are closed. The first type of fields with closed trajectories is characterized by the potential energy that is proportional to the square of the radial coordinate. The second type of fields with closed trajectories is characterized by the potential energy that is inversely proportional to the radial coordinate. The field of the first type corresponds to an oscillator, and the second to gravitational and electrostatic Coulomb interactions.